Hi, I'm Chris, as suggested. I work for a company called Zendesk in the data team, which is aptly named Bunyip. And I'm going to talk today about an end-to-end machine learning ecosystem and how we built it in a quarter, almost. We're pretty close. So, like, just a sort of a brief background. So, I guess the data team at Zendesk, we're pretty interested in building, like everything data-related. That's like data infrastructure. We deal with sort of the big data sort of stuff. We're interested in advanced analytics, machine learning, and generally trying to like turn the data that we have into data product that we can use to sort of build into Zendesk. So, you might be asking yourself why my next slide is not coming up, and I'm not sure either. Okay. So, as I mentioned, I work for Zendesk. I'll give you a brief intro to Zendesk because it kind of gives the context for why we're building this thing in the first place. So, we build software that helps sort of manage customer support. So, kind of like the conversation between a customer and a business. So, when you have like, like a support request, like you left your hat in an Uber or something like that, and you need to write to them and say, "Hello, I left my hat there." It kind of goes through our software and helps manage that communication backwards and forwards. Support software kind of used to look like this. It still does at some places. This might be what you get when you contact your mobile telephone provider and ask for support. It was common case that people use something really clunky like this that made sort of like I guess like this sort of communication backwards and forwards quite. I guess it didn't really flow, right? It kind of stifled the communication, and so. Where we work, we have a much nicer platform for sort of managing this, this communication, and it integrates with a lot of sort of different channels like email and voice and Twitter and so forth. And it's quite lightweight, and it's pretty easy to use for people on both sides. And the idea is that this leads to a better support experience, both for the company and for the customers. So we're a software as a service company, so we're on the internet. And we have lots of customers, about 50,000. They all have their own customers. So we deal with a lot of tickets on a daily basis, which I guess is why we come up with the need for a data team in the first place. Is that we generate a lot of data. So we need people who are interested in taking like this magnitude of records and trying to work out what we can do with it and how we can turn this into something useful. Like what's effectively sort of the exhaust of our actual product and how we can make it do cool things. And that's what our team is interested in doing. So for this talk, the motivation, you can consider this use case. You have a customer who's Marge and a support agent who's Homer. And Marge writes in and says, "Hello, my thing broke." And Homer writes back very quickly, "My apologies, we will fix the thing," and Marge is very happy at the end, right? And this is how you want your support experience to be, right? You want to contact the company that's involved, and you want to tell them your problem, and you want to get an answer, and you want to get it resolved very quickly. The problem is that often it's a little bit more like this, where you contact them and you don't hear anything back, or you hear like back an automated response. It doesn't really answer your question. And you end up sort of feeling a little bit disheartened or angry about the whole sort of process, right? And so as part of having a Zendesk, what you can do actually is you can send out a survey at the end of the support experience and ask your customers how they felt about the process, right? Whether they were happy or whether they were not, right? It's a yes-no sort of thing. And we call this a customer satisfaction survey. And as a result, you can say, "I was happy" or "I was not," and you can give a reason. But this kind of sets you up for like a pretty classic supervised learning sort of problem, right? So we've got a whole bunch of tickets, and then we have a really nice labeled data set where we know whether the people were happy or not. And so you can come to this business question. Can we predict the customer satisfaction for a ticket given the life cycle of the ticket? So given the things we know about the ticket, the text, how long an agent interacted with it, how many different people you had to speak to, when they first responded to you, that sort of thing. And there's a bunch of sort of interesting reasons why you might want to know this. One is that you could infer the queue health, right? So if you're a company and you have 1,000 open tickets where you're trying to support your customers, if we could infer how likely each of those tickets are to get good or bad satisfaction, you could sort of get an idea on how well your support organization is doing at this point in time, right? You could use it for early intervention. So you could take that and you could say, "Here are my 10 worst tickets. I need a manager to go and look at this, right? And to intervene." And you can also use it for automation. So automations would be instead of getting a manager to look at it, you could get a machine to look at it and say, if the likelihood that they're going to have a bad experience is greater than blah, then we should go and do a thing, right? And that's sort of our motivation. And that's what the business question is. But the engineering question is slightly different, right? So the engineering question starts with the business question. Can we predict the customer satisfaction? But given that we can we do this for multiple customers, right? Because each of our customers has sort of like a different sort of user base. They have like different product ideas and so forth. And it's, building a model for these things is going to be quite different, I guess. And then the question is, if we know we can build a model that works, can we actually scale the building of these models? And can we get that into production? So can we integrate it back with our existing product? And I guess the talk today is about that process and what we went through to get there. And it's all in Python, which is why we're giving this talk at PyCon. So, can we predict the customer satisfaction? It turns out we can. We can actually do it quite well. We get quite high accuracy for being able to do this for quite a number of our customers, which is a good thing. So it's a good starting point because it means we're sort of on the right path. So as has probably been mentioned, earlier, and I guess if you're not sort of clear with what I mean by predict customer satisfaction, it's basically we want to take the stuff we know about the ticket. We want to learn some sort of model. We want to project it into some numerical space and learn a model that says, if I draw a line, all the tickets on this side of the line are good and all the tickets on that side are bad. And that's the result we're after. But actually, the process of doing that is quite a bit more difficult, right? So the first step is you've got to get the data. So we need to get this out of our databases. Like having a data team is kind of an afterthought. It's not our main product. So our databases are designed, like at most companies, they're optimized for transactions. So it's a normalized database. So you need to go and we don't just have all of our ticket data in one spot. We have to go and get it from a whole bunch of different places and stick it together. The next thing you want to do is build the features. And this was spoken about earlier. This is like the idea of taking all the things you know about the tickets and turning it into something you want to give to what is effectively just a mathematical equation to say it's good or it's bad, right? And so for some things it's easy, like how long a ticket was open. This is a number, you can put it straight in. Other things are a bit more difficult, like the conversation backwards and forwards, like the actual text, right? You need to turn that into a representation that machine learning algorithms care about. And once you've done that, then you might want to choose a model, like we heard about random forest before, but there's a whole bunch of different models that you might want to use. You want to train it. You need some sort of success metric that says I'm doing kind of okay or I'm doing really well. And then you iterate on that, right? And that's kind of like the data science part of this process. And to do that, we use pandas, which we've heard about before, and I think we'll hear more about throughout the conference. We use scikit-learn, which is a great machine learning library, and we use Jupyter Hub. So Jupyter, for those who don't know, is like the new incarnation of what was IPython notebooks. And it's kind of this cool way of, I guess, documenting a workflow where you can kind of embed documentation and your code together. You can execute the code within the document. It's great for collaboration because people can really read a story of the analytics you did from top to bottom, right? You can say, hey, I'm doing this because of blah, and then you can insert some images maybe, you've got some code and so forth. So it's quite nice, and we use it pretty extensively at Zendesk. Okay, so let's get to how what this might actually look like as a machine learning problem. So this might be the things you know about a ticket, right? You've got a subject, a description, a couple of comments, and then some numeric features that we know about it, like the number of comments, first reply time, and maybe a categorical feature like the requester's user ID, right? So it's a number, but it's not a number in the sense that like a meter 60 tall is bigger than a meter 50 tall, but it's a number in the sense, it's a representation of a category, right? The number represents one user, and it doesn't relate to the user who has the ID, one higher or lower. So we need to be able to take this and we need to be able to turn it into features. So our approach was to break this up into sort of like 3 different workflows. One dealing with the initial ticket details. So at the beginning, we just get in a subject and a description. That's basically all we know about a ticket. Then there's like the textual component, which is like the conversation backwards and forwards. These are the comments on the ticket. And then we have like the metric sets, which are like the metrics, the things that we can measure about a ticket. Okay, so to show you what one of these pipelines look like, we can look a little bit deeper into the comments pipeline, because it's kind of interesting because it deals with both numeric and textual features. So we would take our comments pipeline, which you can see the details at the top. So we got 2 comments and a numeric thing, which tells you how many comments there were on the ticket. And we'd probably split that up into sort of 2 different flows, I guess, right? So building features from numeric features is pretty straightforward. The simplest thing is you just take the number you already have and you're done, right? You can do other sort of fancy things. You could do maybe a polynomial expansion, like take the square of the number or the cube or so forth. You could bin it, so you could maybe create a bunch of bins and say, did this ticket have more than 5 comments or less than 5 comments? Or did it have more than 1 comment, or did it have exactly 0 comments? And you can generate binary features that sort of answer those questions for you. All of those things are kind of interesting representations of a number that you might want to give to a classifier that can help you sort of learn better decision boundaries, better ways of working out whether the ticket's good or bad. With text, text is kind of, it's not really trickier, it's different. In the respect that obviously you can't just take the text and give it to the classifier, because classifiers want numbers, not words. There's quite a few sort of general approaches to how you might convert text into numbers. Like the simplest and most classic is called bag of words, where you effectively just make like a giant dictionary, and you say like each column represents a word, and we just put a 1 wherever we find a word in the document that we're interested in. The others, TF, IDF, and hashing, are kind of variants on that. The thing that you find with text data that's different to sort of the numeric data is the dimensionality tends to be quite high. So when we run sort of our bag of words algorithm, we generate like a sparse matrix that has like about 1 million columns, right? So for each ticket, you suddenly have like 1 million features where you could have 1s or 0s. Whereas from the numeric ones, we don't quite see that sort of expansion. We can take the numbers themselves as they were, so the feature space is quite a bit smaller. Okay, so for each of those, right, we'd split up the pipelines and we would build features, right? So for each ticket, if each ticket was a row, then each column is like a feature, and we have features related to the number of comments and features related to the text, and we can stick those back together to make like a super feature for the ticket that we'll give to our classifier. And that would look something a little like this, right? So we've got, on the very left-hand side, we've got the comments data that comes in. Then we've got, in this case, we choose 3 different pipelines, one where we're extracting TF-IDF features, one where we're doing hashing on the text as well, and the bottom one is just numeric features. And we take those, we do like all the feature extraction, then we combine it back together into sort of one big matrix, and we can pass that on to our classifier so that we can, train it and try and work out whether we can predict a ticket satisfaction or not. If you look at that sort of in code, scikit-learn gives you a really nice ability to build these sort of pipelines as well, right? So this is like the code equivalent of the diagram we saw on the last page, where you've got the top line is like select features out of the data that we have, then do a feature union, so like a union on like a bunch of different feature extraction things that we want, where we can say which column we want to extract the feature from and what we want to do with it. So we've got like a TF-IDF transformer, a hash transformer, binning transformers. We stick all of that together and we throw it at a model. In this case, logistic regression, because it works and it's super simple, basically. So some of this stuff is straight out of scikit-learn, and some of the stuff we've sort of written on top. So we've sort of extended a little bit, written some of our own transformers, our own way of building pipelines a little bit to make this process a little bit easier for us to iterate on. Okay, so that's kind of what the comments pipeline looks like, but we've got the initial ticket, and we've got the ticket metric, so we've got these other 2 pipelines, and we've got to kind of do the same thing with all of those, and we want to bring all of that back together. And that would look a little bit like this. It's very similar to the last diagram, right? We have all of our ticket data. They get split up into each of the 3 different pipelines where we do feature extraction. We train a classifier, and that classifier learns how to predict the ticket satisfaction based on those features. And we do that individually for the initial information, the comments, and the metrics, and then we combine them back together using just, in our case, actually just taking the mean. And often that works quite well. This is another form of ensemble classification. It's similar to like random forest, what we heard before. So we've got a bunch of different classifiers. We ask them all what they think. We stick it together, and we sort of go, we'll take the average, and that's pretty good. And it turns out that's quite okay. The interesting thing is there's a lot of parameters to tune here, and I'll come back to that later. But each of the feature extractors, each of the classifiers themselves all have their own parameters. On top of that, there's like the process of choosing which features you might actually want to use, right? So there's kind of a lot of moving parts, a lot of things to tune. Okay, which brings me to the next thing. Can we automatically tune your models? So using what I've described so far, we can build a model that will predict quite well for a single customer. We started with ourselves, like whether we can predict the satisfaction of our customers when they communicate with us, and that worked quite well. So then the next question is, okay, so far it's been me sitting at a computer, or me and some colleagues sitting at a computer and like tuning these algorithms and saying, well, what if we do this instead of that, and what if we change this parameter to this, and so forth. But if we want to scale this to do it for 50,000 of our customers, obviously we can't hire that many people to sit in front of computers, right, and tune these models. So we need to automate the process. And the scale of the problem is maybe not apparent if you sort of look at it at the beginning, but if you think, for example, that we have 50 different parameters that we might want to tune, and maybe we have 5 options for each of these parameters, like 5 values that we can choose. Some of them have more, some of them have less. But if we go with the number 5, that gives us this number at the bottom, possible combinations of how we could set up these models, right? So this is a really big number. You can't we saw an approach of like tuning parameters earlier, which is called grid search, where you go through each possible combination. This is not an option for us, right? Because the combination is massive. And actually, this combination is so big that it caused, it broke scikit-learn when we started doing it, because basically, if you try to use, scikit-learn has like a thing called a grid search, right, which will do this for you, but the problem is that it tries to build all of these parameter combinations in advance before actually starting the search, if you don't tweak it properly. There's a bug in the code. And basically, we were finding we'd kick off the thing and we'd be like, all right, it's going to run, and then we'd just run out of memory. So you can kind of get around that in a weird way. Hopefully, that'll be fixed soon. I think there's a fix in master. So basically, the way we go and we build these models then is instead of using a grid search, we use what's called randomized cross-validation. So basically, instead of trying to search all of the possible parameter combinations, we just draw a random sample of them, n random samples. In our case, maybe 10, 20, 30, whatever it might be, right? So we go for each of the parameters, we'll just draw a random value of it, we'll stick it together, we'll put that into the classifier, we'll train it, we'll see how it goes, we'll do it again, we'll do that 10 times with random draws, and then we'll just take whichever one's the best, and we say that's a pretty good estimate of how well we can do. And that's kind of what you see here. So we have the data that goes in. We've got our 3 pipelines where we sort of tune the parameters. We do that 10 times, 20 times, and we say, OK, this is the best model we found. We take that one. We combine them together. And we save the model. We say that's the best. And that's almost good, except that if you do that today and you do it tomorrow, and you're only sampling, say, 10 times out of this space of 5 to the 50 possible parameter combinations, there's a chance that what you come up with tomorrow is worse than what you had yesterday. So we have to add a step that basically says, compare the new model that we found to the last model that we thought was the best and see. And we just keep the best one out of that. So it allows us to sort of iteratively search this parameter space really, really slowly over time. And this process basically allows us then to scale our model search so that we can do this for all of our customers, given a reasonable amount of computing resources, right? So this whole process that we've done so far gave birth to a project called Selfie for self-learning machine learning. And basically, this is kind of like a framework or a wrapper that we've built on top of scikit-learn that allows you to sort of specify like these combinations of pipelines that I've been talking about, like the way that you have your original data, you might split it up into subsections, you might split those up further and have a whole bunch of feature transformers, a whole, a quite large parameter space that you might want to search, and you can just sort of say, here's a relatively chunky computer, just go and find me a pretty good version of this model without actually having to go and do it yourself. Yeah, so that was quite fun to build. I don't know. It's shown to be pretty useful so far. So we've gotten to the part where we are like, okay, can we do the problem? We can predict a customer satisfaction given the information on a ticket. We know that we can do this for multiple accounts without having to scale manpower very much. But the question is, like, how do we build all of these models, right? It's still, building 50,000 models, it's relatively computationally expensive. Where do we get the computational resources, and how do we make sure this works? And basically, we abuse Hadoop to do this. So we have an existing Hadoop infrastructure that we use for a lot of our sort of ETL and tasks and various other sort of like aggregations and statistics and other things that we sort of integrate back into our product. This is built on using Cascalog, which is sort of like, it's a closure framework that sits on top of cascading, which is basically a way of being able to use MapReduce without ever having to write Java, which is a good thing. And we abuse the resilience, I guess, in job tracking of Hadoop to run our Python processes individually on each of our data nodes. And so what that means is basically we use Hadoop to get all the data together, send it to a bunch of data nodes, and then start up our Python processes outside of the MapReduce framework. They find a good model, they save it to disk using Pickle. I don't know if you've heard of Pickle before, probably, maybe. It's a really nice way of being able to save things to disk in Python. It works with scikit-learn models, so you can train your model, you can save it to disk, and you can open it up somewhere else and use it, which is a very useful thing if you want to train a model here and maybe use it in a product over there. So basically, MapReduce just starts up our process, our model gets trained, it gets sucked back into HDFS, and then we have like, in our Hadoop cluster, we have like all of the information about the various models that we've trained. We've got logging and so forth. And the thing that Hadoop gives us is scheduling, failure handling, and job retries, right? So if we're trying to build these thousands of models, if one of them dies, we don't want to have to care about that personally, and we don't, because Hadoop manages that for us. It knows to restart the training maybe somewhere else if the data node has gone down or so forth, right? And this allows us basically to save the models and then ship them around somewhere else. So it sort of gives us the scaling that we need. Another cool Python thing that we actually use to schedule this is called Airflow. It's built by Airbnb, and it's like a task scheduler, I guess, and we use that to run all of our jobs on our Hadoop framework. Okay. Production. So we know we can build a model that works. We know we can do that for lots of customers. We even think we know where we might actually build the models, but then the question is, how the hell do you take a machine learning model that's written in Python and make that accessible to our product, which is mostly built in Ruby? That's a good question. Mostly, we want it to be kind of magic, right? We don't want the rest of our product to have to know about it. We effectively want an API that you can hit and say, dear API, here is a bunch of ticket information. You tell me how likely it is that this ticket is going to have good satisfaction or bad satisfaction. And our API in the background is going to load our pickled model. It's going to run the data through the model. It's going to make a prediction, and it's going to send the information back. And the rest of the Ruby world will sort of be none the wiser of what's going on in the background. So we built a thing called Crystal Ball because you can ask it questions, and it gives you answers about the future. And it is basically this cool interface that hides all of the hard work that we've done in the past. And it's actually, there's not even really much to talk about here because it's super simple. It's like, it is the most simple Flask API you've ever seen, except for a couple of caveats. It's got some interesting caching on there because these models are pretty big on disk, in the hundreds of megabytes. So we don't want to have to, each time we get a request for a different account, we don't want to have to go and load that account's model off disk because it's going to be slow. And the sort of servers we run it on are probably a little bit different to our normal web servers just because of the memory requirements. So, but outside of using a bit of caching, running it on a web server that's slightly bigger than what our normal web servers look like, this is basically a really straightforward API. And the reason that it's so easy to integrate, to build such a straightforward API is because the Python framework from the start to the end, everything's compatible, right? We just write out a pickle. Python running with Flask also knows how to read this thing. It doesn't have to know how we built the model. It just sort of imports scikit-learn and it does its thing, which is pretty nice. So a post and a response looks something like this, a whole bunch of information in a JSON document. We get back a thing saying probability of good customer satisfaction is 0.99. So that's like, that's a happy customer, I guess. Okay, so that's kind of what we've done. The future is we would like to open source Selfie, get other people to start using it, get them to try and benchmark it. We'd like to play with Kaggle competitions using it. We haven't really had the chance to do that yet, but it's on the list of things to do. And hopefully once other people start using it, they can also give us feedback on how we can make it better, right? And another interesting thing I think to do in the future is also doing model interpretation. So at the moment we can build a model that says, given this ticket, we think the probability of it, having good customer satisfaction is blah, but we can't really tell you why we think that. And there's certain ways that you can interrogate these models, basically to get a good feeling of sort of how they respond to different parameters changing and so forth. So I'm almost done. That says thanks, but I have a couple more points. So the question is, how do we manage to build this in a quarter? I think it's kind of a lot of work to get done in a quarter, and the main reason that we were even able to come close, because we didn't quite make it, but we were so close. And I had to give him the title of this talk before I actually knew whether we were going to finish or not, is because everything was in Python. And it really, I think just the ability to build your models over here and ship all of that stuff around the place to get it to run on Hadoop, all within one framework allowed us to sort of iterate very quickly on building these models and the great data stack that's available in Python through pandas and scikit-learn and numpy and scipy gives you all the tools you need to build these sorts of things. And the idea is that this is our first pass, but in the future it gives us a platform that we're going to be able to build on. Next time we go to build a new machine learning model to predict something else, all of the infrastructure is there. We just need to build the thing that builds the model, and it will just flow through and come out through our API, and life will be good. Aside from that, we're hiring. So if you want a data job, come and see me, or email me, or look at the jobs thing. That's it. Questions?
Thanks for the talk. How much do you find the models change between customers?
They change a fair bit between customers, but to be fair, they change a fair bit between any given run on training on the same customer because we're sampling from such a huge parameter space. So it's something that we haven't investigated a huge amount, but there's definitely differences between the parameters for sure. How much of that is meaningful and how much is not so important to the end result of the model, I think we haven't dug into that far enough yet.
Okay, any other questions?
On a related question, it sounds like you're keeping the data from different companies very separate. Is that for practical reasons or for commercial sensitivity reasons?
Both, probably. Well, yeah, both. I think, obviously, commercial sensitivity, it's not our data to share with other people, obviously, even sharing in a model that no one else is going to see, so we don't want to do that. On top of that, I think the sort of questions, like the support tickets that you would get if you're a university are very different to the support tickets you would get if you're Airbnb, right? So, and probably the expectations of the people submitting those things and therefore the things that will drive whether it's good or bad satisfaction will also be different. So I think like the differences in domain between our customers probably mean that having like a generalized model is probably not going to work that great.
Yeah, with respect to the parameter search, have you considered some kind of gradient descent method or?
Yes.
Yes?
We haven't done it yet though. Mostly because this is out of the box in scikit-learn and it works. There's a whole bunch of literature around like better ways than this to look for parameters in a huge parameter space. I think when we get to the point that we need to do that, it's certainly on the list of things to do.
Thanks for the talk. Just a quick question about your use of Pickle. We've come across the same problem with shifting scikit-learn models around, and it always terrifies me a little bit that we're forced to use Pickle rather than just being able to pop out the parameters, shift the parameters somewhere and do it again. So have you run into any problems using it, like version mismatches?
Not so far, but so our versions are all managed by this, everything's managed through Chef. So theoretically, all of our environments that have to deal with this have the exact same Python setup. Yeah, I hear you, right? Like shipping the parameters is probably a nicer way to do, a nicer thing to do, and it's something that we could write into this because of like the structure of the model the way it is at the moment. It's not super easy to just go drop all the parameters and rebuild from all the parameters, but it'd be a nice thing. We started using the joblib dump, which is like which you also get through scikit-learn. Problem is it creates one pickle file or one numpy file per array that exists within your whole model. So you end up with like 1,000 files for your one model, which is also painful to ship. So Pickle kind of does the job for the moment.
Hi, thanks for your talk. It was very interesting. I just want to ask, does your tool take into account that the model may evolve temporarily?
That is exactly the idea. So we rebuild this on a regular basis. So maybe like once a week for each account as like new, we're getting more and more information all the time, right? So we want to rebuild it all the time, and that's kind of part of the reason why we do this comparison to the previous model as well, because the new model we build might still not be better than the last one that we had, and it depends on how the data might change over time.
But is it also possible that the way people behave itself changes?
Totally. So if you're a company, for example, and you release a new product that didn't exist last week, you'll end up with a whole bunch of support tickets talking about something you never knew about before, right? So there's going to be there'll be big changes to the dynamics of how the model will predict what's good and what's bad.
Hi, so it sounds like you set up quite a lot of machinery there to get the job done. Do you have any kind of simplified model that you use to evaluate your performance against a baseline to kind of prove the need for that much work?
We did build a pretty simple model at the beginning. It didn't work very well. I don't think we don't rebuild that on a regular case because the difference was significant. But we're certainly open to like evolving, like the number of pipelines we need, what sort of feature extraction we use. And I think at the moment we've been like, let's get something that works as well as we can think of, and then the next stage is also pair that back and actually make it like, minimum viable product, I guess, in that respect.
I don't know how relevant this question is, but what is the sample size before you actually decide the customer response is right or wrong for a certain product for the company?
You mean what's
how big is your sample size? What is the power of the stats?
So training examples, do you mean?
No, I mean, how many number of people have to respond so that you get something relevant out of it? In terms of yes and no, I mean, this is not a good service, this is not a good product. How many number of customers are kind of responding?
So it's not so much to do with a particular product, but to an individual support experience. So each one is like a sample of n equals 1, I guess, because it's sort of, the way I write to this company and talk about my particular problem is going to be different to the way anyone else did. As far as like how much data we use to build the models, it depends on how many tickets accounts get. This can be anywhere between a couple of thousand to hundreds of thousands or millions.
Hi, I'm not really an expert on this stuff, but did you say that it was a purely random where you assign your parameter optimization?
Yeah.
Did you consider going down the route of using the previous one and weighting what you thought was important to reseed those randomness?
So we could totally do that. Basically, we just did that at the moment because it's out of the box and it seems to work pretty well. There's certainly ways we could improve on it. I mean, at the moment, it's a random walk in like, I don't know, 50 dimensions. It's not super efficient.
Yeah, okay, cool.
I just wondered out of curiosity what sort of accuracy you're receiving from your predictions.
So we use ROC, AUC, so like the area under the curve for the receiver operator characteristic. But I don't know. This is basically a way of measuring like where the your trade-off between true positives and false positives and so forth. For some accounts, we get up to like 0.99, so basically perfect. Other accounts, it's a bit less than that, like in the 0.8 sort of range and in between. So it works pretty well. There's definitely well above chance. We can give it a bit of a push for some accounts, though, I think.
So the classifier output is like the probability of them being in the like happy class.
Exactly.
Given that I'm an end user of your software, not the person with the issue, but the Airbnb or whoever.
Yeah.
How do they actually use that information? Do they, if it predicts a negative experience, they go and try and intervene and make it a positive experience?
Yeah,
is that the idea?
That's up to the individual accounts. We make the information available. That's certainly one of the options that they could do. You can use it for monitoring. You can use it for intervention, for automatic routing of tickets. Basically you can build it into the workflow like anything else that exists in a Zendesk.
How do you handle customers who have different types of tickets? For instance, maybe ones that are, maybe some of them are super long and will involve a number of different replies, whereas others are really easy ones that you can just solve in a single reply.
At the moment, we throw them all in the same bucket and hope for the best. There's definitely something to be said for trying to split those things out. Again, this is kind of first pass. It seems to work pretty well at the moment. I think as we dig into the customers that don't work or the ones that don't work as well as some others, I think these are the sort of things we're going to find. It's quite common that you'll have more than one complaint in a given ticket. That said, I think a lot of the driving factors around whether someone is happy or not is to do with the sentiment of the conversation backwards and forwards, and I think that probably doesn't scale too badly with even the size of the ticket.